Hello and welcome to this Vivado quick take video. In this video, you'll learn how to create an AXI peripheral to which custom logic can be added to create a custom IP using the create and package IP feature of Vivado. This training assumes that you are familiar with designing IP subsystems in IP Integrator. You can watch some of the quick take videos on IP Integrator as shown on this slide. In this quick take video, we'll create a new project in Vivado. Using the create and package IP feature, we will then create a slave AXI peripheral. We'll create a test bench and the necessary drivers for the peripheral for developing a software application in SDK. We'll simulate the AXI peripheral in Vivado to ensure that the registers of the AXI peripheral can be written and read from using an AXI bus functional simulation model. Then we'll create a microplane processor-based system in which we will add this custom IP. The design will be then implemented and bitstream generated. We'll then export the hardware to SDK and create a test application and generate an ELF file. Finally, we will launch our application on the target board KC705 and verify its functionality. We start our design by launching Vivado and creating a new project from the Quick Start page. We'll name the project and specify the location where the project will be saved. We'll skip some of the other options for adding existing RTL, IP constraints to the project at this time, as everything needed for this project will be generated later. We select boards in the default part page. Vivado is board aware, and it knows the physical connections present on our target board. It can thus generate the appropriate physical and timing constraints for our target board based on the interfaces that we choose in our design. We select the KC705 target board here. Let's review the summary screen to make sure that all the options have been entered correctly and click Finish. Once the project has been created, we launch the Create and Package IP feature. Using this feature, you can either package a new IP or you can create a custom AXI peripheral to which your logic can then be added to make your own custom IP. When you launch the Create an IP package feature in a new project, you have two choices. You can either package a pre-existing project directory or you can create a new AXI4 peripheral. We choose the Creating a new AXI peripheral and click Next. In the next page, we can specify several options such as name, version, display name, description, and the location where the IP will be created. Once the IP is created, you can search for the IP in the IP catalog using the name given to this peripheral. Also note down the IP location. This is where the IP repository is created. On the Add Interfaces page, you choose the number of interfaces that you want the AXI peripheral to have. Interfaces can be added by clicking the plus sign and deleted by selecting the delete icon. Notice that the component symbol also gets updated as you add and delete interfaces. Several properties of the AXI4 peripheral can be specified on this page. You can specify the name of the AXI interface in the name field. You can choose the type of AXI4 protocol desired. The choices are light, full, and stream. You can specify whether the interface is created in a master mode or a slave mode. You can also specify the data width for the interface and the number of registers desired. Currently, the number of registers supported by this feature for AXI Lite interface is between 4 to 512. For the purposes of this video, we'll go with the default values. Click Next to get to the Create Peripheral Summary page, where you can either add the IP to the repository or edit the IP further to create a custom IP. You can also create a test bench to verify the AXI4 peripheral using an AXI bus functional simulation model, or you can test the IP in hardware by using the JTAG to AXI IP core. In this case, we will select the Verify Peripheral IP using AXI4 BFM simulation interface option and click on Finish to create the AXI peripheral. As you notice, a block design is created and AXI peripheral is instantiated and connected to the AXI bus functional model. The design is then elaborated and simulation is launched. The test bench that is created with this design exercises the bus functional model to generate several read and write transactions. Those transactions can then be verified in the simulation window as well as on the Tickle console where the result of read-write transactions are written out. Take a moment to look at the waveform window and also the Tickle console to verify that write and read operations took place all right. You will notice several statements in the Tickle console showing the data written to the peripheral and the data read out from it. If adding custom logic to this peripheral is desired, you can add your custom logic to this peripheral at this time. The peripheral can then be repackaged to turn it into a custom IP. At this point, we can close the simulation and exit project. Click OK to exit from Vivado. Next, we will create a new Vivado project to create a microplane-based system in which we will instantiate the AXI peripheral that we just created. Again, like before, we'll create a Vivado project using the default settings and making sure that we target it to the KC705 board. Take a moment to review the new project summary page to ensure that all the project settings have been entered correctly and click Finish. Once the project is created, we need to create a block design. We give a name to the block design and click OK. In the block design canvas, we instantiate a microplane processor. Notice that as the processor is instantiated in the diagram canvas, designer's assistance becomes available to us. Click on the link to use the block automation. In the Run Block Automation dialog box, we'll increase the depth of the memory to 32 kilobyte and let all the other remaining options to their default value. Once the basic subsystem is created, we can instantiate the AXI peripheral that we had created earlier. To make the AXI peripheral available in the IP catalog, we need to add the repository containing this IP to the Vivado project. We do this by clicking on Project Settings under Project Manager and then selecting the IP icon in the left panel. Click on IP Repository and then browse to the repository called IP Repo and click Select. As soon as the IP repository is added to the project, you can see the AXI peripheral called MyIP that was created earlier. Let's instantiate this IP now, along with an UART Lite IP in the design. The UART Lite is necessary to monitor communication between the hardware and software on a terminal window in SDK. You will notice that Designer's Assistance is available again, which we can use to make quick connections of the newly instantiated IP to the microplane subsystem. As mentioned earlier, Vivado is board aware and knows the interfaces present on the KC705 board. As we use the Designer's Assistance to make connection to the different interfaces on the board, you will notice that the interfaces that are used in the design show up in the Connected Interfaces folder in the Board Part Interface window. We only need to use the clock reset and the UART interfaces in this design. Use all of the items under connection automation link to complete the connectivity of the design. With the design now complete, let's make sure that the memory mapping for all the slaves in the design has been done correctly. As the slaves are instantiated in the design, IP Integrator assigns the memory to each of these automatically. This memory mapping can be changed if desired. In this case, we'll leave the default memory map. At this point, we're ready to validate the design. Validating runs design rule checks on the design. Running DRC is successful and there are no design errors in this case. We can tidy up the design and generate an optimum layout of the design by clicking on Regenerate Layout. At this time, we can save the block design. With the block design now complete, we generate output products and create a top-level wrapper file that instantiates the block design in it. Now we need to implement the design, which can be done by clicking on Generate Bitstream, which will take the design through synthesis, implementation, and finally generate bitstream. Generating the bitstream may take several minutes. After bitstream has been generated, open the implemented design. Once the implemented design is open, run a timing summary report to make sure that all constraints were met. Take a moment to look at any setup or hold time violations. In this case, everything is good. So we need to export the hardware so we can develop our software application. To do this, we'll export the hardware by selecting Export Hardware for SDK. While exporting the design, we selected the option to launch SDK. So SDK launches in a new window. In SDK, we'll create an empty application project to which we can add some code to exercise the AXI Peripheral on the KC705 target hardware. Let's create an empty application first by creating a new application project and specifying a name for the project. In the template space, select Empty Application and click Finish. While creating the empty application, SDK creates a self-test application for the AXI Peripheral, which we created in Vivado earlier. This self-test functions need to be called by our custom application code. So essentially what we'll be doing here is just add a few lines of code in our application to call the function that performs the self-test of the IP. This self-test routine, called myIP_self_test, basically writes 4 bytes of data and reads back those data bytes. So we'll add a new file. We'll call this file main.c. In this file is where we will add the few lines of code to call the function that was created earlier for exercising our AXI Peripheral IP. Now we are ready to compile this code. Once compilation is done, take a moment to look at the console for any warnings or errors that may have been flagged during the process. In this case, it appears that everything is good. So we'll connect the monitor to monitor the communication between the hardware and the software. With the monitor connected, now we're ready to program the FPGA. Make sure that the bitstream selected is the correct bitstream for the project. Programming the FPGA may take a minute or so. Now that the FPGA has been programmed, we can launch the ELF file onto the hardware. To do this, we'll select the application code that we just created and launch it on hardware. On the bottom right of the window, you can see that the code is being launched on hardware, and on the terminal you will see the results of the self-test that was performed. The terminal window shows that 4 write transactions were performed, followed by 4 read transactions, and the data for the write and read matches. So in this quick take video, we have created a new AXI peripheral, simulated it using an AXI bus functional model, and then verified its functionality on the KC705 board in a microplane-based design. We have seen how the create and package IP functionality in Vivado allows you to create a master or a slave AXI peripheral, which can be used to create a custom IP. Thanks for watching the quick take video.